it is accurate to state that a 400 amps fuse appears excessively high for protecting number 4/0 MV-90 conductors. The conductor ampacity is 235 amps, and National Electrical Code Section 240.101 permits a fuse rating of up to 3 times the conductor ampacity for circuit voltages greater than 600 volts. However, this allowance is exclusively for overcurrent protection of the conductors. In this particular scenario, the fuse is tasked with providing short-circuit protection to the conductors. For short-circuit protection, the fuse rating must be restricted to the maximum short-circuit current that the conductors can safely endure. This value is typically determined by the available fault current at the fuse location. The available fault current is likely to be significantly greater than the conductor ampacity. Consequently, a 400 amps fuse rating is likely too high to offer adequate short-circuit protection for the number 4/0 MV-90 conductors. A lower fuse rating, such as 300 amps, would be more suitable. Overloads that notably exceed ampacity ratings are permitted in this instance due to the conductors being shielded from short circuits by the fuse. The fuse will activate and interrupt the circuit if the current surpasses the short circuit rating of the conductors, thereby safeguarding them from potential damage. The installation aligns with the National Electrical Code stipulations only if the fuse rating is capped at the maximum short-circuit current the conductors are capable of withstanding. This determination is typically made based on the available fault current at the fuse's location. To elaborate further, firstly, it's crucial to understand the roles of overcurrent protection and short-circuit protection. Overcurrent protection safeguards conductors from prolonged overloads that could cause overheating and insulation damage. Short-circuit protection, on the other hand, is designed to quickly interrupt very high fault currents that could occur during a short circuit, preventing catastrophic equipment failure and potential fire hazards. Secondly, National Electrical Code Section 240.101 provides specific guidelines for overcurrent protection of conductors rated over 600 volts. It allows for higher overcurrent protection device ratings under certain circumstances, recognizing the different characteristics of high-voltage systems. However, this allowance does not negate the need for adequate short-circuit protection. Thirdly, determining the appropriate fuse size involves a comprehensive analysis of the system's characteristics, including the conductor ampacity, the available fault current, and the interrupting rating of the fuse. The fuse must be capable of interrupting the maximum available fault current without failing, while also providing adequate overcurrent protection for the conductors. Fourthly, the conductor ampacity, as listed in Table 310.77, represents the maximum current a conductor can carry continuously under specific conditions without exceeding its temperature rating. This ampacity is based on factors such as conductor material, insulation type, installation method, and ambient temperature. It is essential to select conductors with an ampacity sufficient to handle the expected load current, while also considering directing factors for ambient temperature and the number of conductors in a raceway or cable. Fifthly, the available fault current is the maximum current that can flow during a short circuit at a specific point in the electrical system. This current is determined by the voltage and impedance of the power source, as well as the impedance of the conductors and equipment in the circuit. A short circuit study is typically conducted to determine the available fault current at various locations in the system. Sixthly, the interrupting rating of the fuse is the maximum fault current that the fuse can safely interrupt without failing. The fuse must have an interrupting rating equal to or greater than the available fault current at its location. Selecting a fuse with an inadequate interrupting rating can result in a fuse failing to clear the fault, leading to equipment damage and potential safety hazards. Seventhly, in the case of the 4160 volts chiller circuit, the 400 amps fuse rating may be too high to provide adequate short-circuit protection for the number 4/0 MV-90 conductors. The available fault current at the fuse location is likely to be significantly higher than the conductor ampacity of 235 amps. Therefore, a lower fuse rating, such as 300 amps, may be more appropriate. Eighthly, to determine the appropriate fuse size, a short-circuit study should be conducted to determine the available fault current at the fuse location. The fuse should be selected with an interrupting rating equal to or greater than the available fault current, while also providing adequate overcurrent protection for the conductors. Ninthly, the National Electrical Code provides additional guidance on overcurrent protection in Article 240, including specific requirements for fuses, circuit breakers, and other overcurrent protection devices. It is essential to consult the National Electrical Code and other applicable standards to ensure that the electrical system is designed and installed in accordance with all applicable requirements. Tenthly, in addition to the fuse rating, it is also important to consider the time current characteristics of the fuse. The time current characteristic curve shows the time it takes for the fuse to open at different current levels. The fuse should be selected with a time current characteristic that provides adequate protection for the conductors and equipment in the circuit. 11thly, the use of molded case circuit breakers in high voltage systems requires careful consideration due to the potential limitations in interrupting high fault currents. While molded case circuit breakers are commonly used in low voltage applications, their application in high voltage systems may be restricted by their interrupting capacity. It is essential to verify that the circuit breaker has an adequate interrupting rating for the available fault current at its location. 12thly, the selection of overcurrent protection devices for high voltage systems should be based on a comprehensive engineering analysis that considers the specific characteristics of the system, including the conductor ampacity, the available fault current, and the interrupting rating of the protection devices. Consulting with a qualified electrical engineer is recommended to ensure that the electrical system is designed and installed in accordance with all applicable codes and standards. 13thly, the NEC permits the use of inverse time circuit breakers for motor circuits, which allow for short duration overloads during motor starting. This is outlined in NEC section 430, which provides specific requirements for motor circuit protection. Inverse time circuit breakers are designed to trip faster as the current increases, providing protection against both overloads and short circuits. 14thly, the NEC addresses conductor protection in Article 310, which covers conductors for general wiring. This article specifies the allowable ampacities of conductors based on their size, insulation type, and installation method. It also includes dirting factors for ambient temperature and the number of conductors in a raceway or cable. 15thly, for high voltage installations, it is crucial to consider the effects of voltage drop on system performance. Voltage drop occurs when current flows through a conductor, causing a reduction in voltage at the load end. Excessive voltage drop can lead to equipment malfunction and reduced efficiency. The NEC recommends limiting voltage drop to a maximum of 3% for power circuits and 5% for lighting circuits. 16thly, the National Electrical Code emphasizes the importance of coordination between overcurrent protection devices to ensure selective tripping. Selective tripping occurs when the overcurrent protection device closest to the fault clears the fault, while upstream devices remain closed, minimizing the extent of the outage. Coordination studies are typically performed to determine the appropriate settings for overcurrent protection devices to achieve selective tripping. 17thly, the NEC requires that all electrical equipment be listed and labeled by a recognized testing laboratory, such as underwriters' laboratories or electrical testing laboratories. Listing and labeling indicate that the equipment has been tested and meets applicable safety standards. It is essential to use listed and labeled equipment to ensure the safety and reliability of the electrical system. 18thly, regular inspection and maintenance of electrical equipment are essential to ensure its continued safe and reliable operation. The NEC recommends performing regular inspections to identify and correct any potential problems such as loose connections, damaged insulation, or overheating components. Maintenance activities such as tightening connections, cleaning equipment, and replacing worn parts can help to prevent equipment failures and extend the life of the electrical system. 19thly, the selection of conductors for high voltage applications requires careful consideration of the insulation type and voltage rating. The insulation must be suitable for the operating voltage and environmental conditions. The NEC specifies the allowable insulation types for different applications and voltage levels. 20thly, The grounding of high-voltage systems is critical for safety and proper operation. Grounding provides a low-impedance path for fault current to flow back to the source, allowing the overcurrent protection device to quickly clear the fault. The NEC provides detailed requirements for grounding systems, including the size and type of grounding conductors, the location of grounding electrodes, and the bonding of non-current carrying metal parts. 21st, the use of surge protection devices is recommended to protect electrical equipment from voltage surges caused by lightning strikes, switching operations, and other disturbances. Surge protection devices divert the surge current to ground, preventing it from damaging sensitive electronic equipment. The NEC provides guidance on the selection and installation of surge protection devices. 22nd, for high voltage installations, it is important to consider the effects of corona discharge. Corona discharge is a phenomenon that occurs when the electric field around a conductor exceeds the dielectric strength of the surrounding air, causing ionization and a faint glow. Corona discharge can lead to energy losses, insulation damage, and radio interference. The NEC recommends using conductors with smooth surfaces and large diameters to minimize corona discharge. 23rd, the National Electrical Code requires that all electrical work be performed by qualified personnel who are trained and experienced in electrical safety practices. It is essential to hire a licensed electrician to perform any electrical work to ensure that it is done safely and in accordance with all applicable codes and standards. 24th, in addition to the NEC, there are other applicable codes and standards that may apply to high-voltage installations, such as the National Electrical Safety Code, the Occupational Safety and Health Administration regulations, and local building codes. It is essential to consult all applicable codes and standards to ensure that the electrical system is designed and installed in accordance with all requirements. 25th, the use of fiber optic cables for communication and control signals in high-voltage systems can help to reduce the risk of electrical interference and improve system performance. Fiber optic cables are immune to electromagnetic interference and can transmit signals over long distances without degradation. The NEC provides guidance on the installation of fiber optic cables. 26th, for high-voltage installations, it is important to consider the effects of altitude on the dielectric strength of air. At higher altitudes, the air is thinner, and the dielectric strength is reduced. This means that the spacing between conductors and equipment must be increased to prevent flashover. The NEC provides guidance on altitude correction factors for high-voltage installations. 27th, the National Electrical Code requires that all electrical equipment be properly labeled with its voltage, current, and power ratings. This information is essential for selecting the appropriate overcurrent protection devices and conductors. It is also important to label all electrical equipment with warning signs to alert personnel to potential hazards. 28th, the use of remote monitoring and control systems can improve the reliability and efficiency of high-voltage installations. These systems allow operators to monitor the status of equipment, detect potential problems, and control equipment remotely. The NEC provides guidance on the installation of remote monitoring and control systems. 29th, for high-voltage installations, it is important to consider the effects of harmonic currents. Harmonic currents are non-sinusoidal currents that can cause overheating of equipment, voltage distortion, and interference with communication systems. The NEC recommends using harmonic filters to reduce harmonic currents. 30th, the National Electrical Code requires that all electrical equipment be installed in a neat and workmanlike manner. This means that the equipment should be installed in a way that is safe, reliable, and aesthetically pleasing. The NEC provides guidance on proper wiring methods, cable support, and equipment spacing. 31st, the use of arc flash protection is essential to protect personnel from the hazards of arc flash events. Arc flash is a dangerous electrical explosion that can occur when a short circuit or other fault creates an arc of electricity. Arc flash protection includes the use of personal protective equipment, such as arc-rated clothing and face shields, as well as engineering controls, such as arc flash relays and current limiting devices. Secondly, for high voltage installations, it is important to consider the effects of transient voltage surges caused by lightning strikes and switching operations. Transient voltage surges can damage sensitive electronic equipment and cause equipment failures. The NEC recommends using surge protection devices to protect equipment from transient voltage surges. Thirdly, the National Electrical Code requires that all electrical equipment be properly maintained to ensure its continued safe and reliable operation. Maintenance activities include regular inspections, cleaning, and testing of equipment. The NEC provides guidance on proper maintenance procedures. Fourthly, the use of power quality monitoring equipment can help to identify and diagnose power quality problems such as voltage sags, voltage swells, and harmonic distortion. Power quality monitoring equipment can provide valuable data for improving the reliability and efficiency of high voltage installations. Fifthly, for high voltage installations, it is important to consider the effects of electromagnetic interference. Electromagnetic interference can disrupt the operation of electronic equipment and cause data corruption. The NEC recommends using shielded cables and grounding techniques to minimize electromagnetic interference. Sixthly, the National Electrical Code requires that all electrical equipment be installed in accordance with the manufacturer's instructions. The manufacturer's instructions provide detailed information on the proper installation, operation, and maintenance of the equipment. It is essential to follow the manufacturer's instructions to ensure the safe and reliable operation of the equipment. 37thly, the use of energy-efficient equipment can help to reduce energy consumption and lower operating costs in high-voltage installations. Energy-efficient equipment includes high-efficiency motors, lighting systems, and transformers. The NEC provides guidance on the selection and installation of energy-efficient equipment. 38thly, for high-voltage installations, it is important to consider the effects of corrosion. Corrosion can damage electrical equipment and reduce its lifespan. The NEC recommends using corrosion-resistant materials and coatings to protect equipment from corrosion. 39thly, the National Electrical Code requires that all electrical equipment be properly identified with its voltage, current, and power ratings. This information is essential for selecting the appropriate overcurrent protection devices and conductors. It is also important to label all electrical equipment with warning signs to alert personnel to potential hazards. 40thly, the use of remote control and monitoring systems can improve the reliability and efficiency of high-voltage installations. These systems allow operators to monitor the status of equipment, detect potential problems, and control equipment remotely. The NEC provides guidance on the installation of remote control and monitoring systems. 41stly, for high-voltage installations, it is important to consider the effects of voltage imbalance. Voltage imbalance can cause overheating of motors and other equipment, leading to premature failure. The NEC recommends using voltage imbalance protection devices to protect equipment from voltage imbalance. 42ndly, the National Electrical Code requires that all electrical equipment be properly grounded to ensure the safety of personnel and equipment. Grounding provides a low impedance path for fault current to flow back to the source, allowing the overcurrent protection device to quickly clear the fault. 43rdly, the use of surge arresters can protect electrical equipment from voltage surges caused by lightning strikes and switching operations. Surge arresters divert the surge current to ground, preventing it from damaging sensitive electronic equipment. 44thly, for high-voltage installations, it is important to consider the effects of harmonics on power quality. Harmonics are non-sinusoidal currents and voltages that can cause a variety of problems, including overheating of equipment, voltage distortion, and interference with communication systems. Harmonic filters can be used to reduce the levels of harmonics in the electrical system. 45thly, the National Electrical Code requires that all electrical work be performed by qualified personnel who are trained and experienced in electrical safety practices. It is essential to hire a licensed electrician to perform any electrical work to ensure that it is done safely and in accordance with all applicable codes and standards. The selection of overcurrent protection for conductors in high-voltage systems necessitates a detailed understanding of both overcurrent and short-circuit protection principles, along with careful consideration of the specific characteristics of the installation.